Welcome to part one of our lecture video series for Friday, April 28th, where we introduce the topic of the idea of the standard enthalpy of formation, delta H sub F raised to this naught, like 4 naught, N-A-U-G-H-T, up here in the superscript. So before we get into any of the thermodynamics or thermochemistry of standard heats of formation, let's remind ourselves of exactly what's going on in a chemical reaction, because that will help us kind of understand conceptually why the standard enthalpy of formation is something that is useful to us when trying to determine the heat of reaction. So recall, what happens in a chemical reaction? So from Dalton's atomic theory, just remember, we know now that a chemical reaction involves first the breaking of existing chemical bonds. This is typically something that requires energy. I mean, it always requires at least a little bit of energy, but it typically requires a lot of energy. And once we have then broken or severed those bonds between atoms, we see that atoms rearrange in 3D space and couple with other new atoms. And then lastly, new bonds are formed between our rearranged atoms. This is where the idea of the enthalpy of formation comes in. We have to remind ourselves that in order for a substance to be made, to be formed, we're talking about the energy that's involved in the formation of those bonds, like how much energy is required to create a bond between sodium and chlorine, how much energy is released to create a bond between oxygen and hydrogen and water. So let's define the standard enthalpy of formation. Delta H sub F, so it's the heat of formation, naught means standard. So again, we've got standard here with this little naught. We've got enthalpy, here are delta H, and then of formation. That's that subscript F. So standard enthalpy formation. This is the amount of energy heat that is either required or released to form 1 mole of a substance at standard conditions. So standard conditions, these are things that we're going to see come up a lot when we talk about gases next week, but in general, standard conditions are at standard temperature and pressure. So let's see here, this is 298 Kelvin, 1.00 atmosphere. So the Kelvin is our temperature, the atmosphere, this is our pressure, right? We're talking about formed at atmospheric pressure. If we are a solution, then our concentration at standard conditions is assumed to be or presumed to be 1 molar. So that is the standard enthalpy of reaction, or standard heat of formation, excuse me. Standard heat of formation. Amount of heat required or released to form 1 mole of a substance. So for example, let's look at how we might make something like sodium chloride from its constituent elements of sodium and chlorine. So if we were to look at sodium chloride's formation, we would look at the reaction of, not that, elemental sodium metal with chlorine gas, which is again one of our homonuclear diatomic elements, to form solid sodium chloride. Okay, now if you and I were to balance this, like this is our typical kind of balanced reaction, then we would see that we've got 2 chlorines here on the left, meaning we need 2 on the right, so we would have to double the sodium chloride, in turn requiring us to double the sodium. However, the standard heat of formation of sodium chloride, as with for any substance, is always determined by the formation of 1 mole of substance. So the reaction that shows the formation of 1 mole of NaCl is where all of these coefficients are cut in half, because I cannot be making 2 moles of sodium chloride if I'm looking at the formation or the standard enthalpy of formation of sodium chloride. I need to be looking at the formation of simply just 1 mole. So cutting all of these in half, this would be 1 sodium in proportion with half chlorine gas to form NaCl solid. And if this is carried out at standard temperature and pressure, at standard conditions, then we find, as tabulated from people that have found this thermodynamic data, that the standard heat of formation of 1 mole of sodium chloride is, let's look that up. So here, I've got somewhere in here a list of common heats of formation. No, it's not that table. I think it's this one. Yeah. Okay, so I know this is really tall, really tiny. But let's see here. We're looking for sodium chloride solid. And we see that the standard heat of formation expressed in kilojoules per mole, because it's always again relative to per 1 mole of substance formed. We see that the standard heat of formation of 1 mole of sodium chloride is negative 410.9 kilojoules per 1 mole that's formed. And this is ultimately an exothermic process, meaning that the formation of sodium chloride solid from its constituent elements is one that releases heat, meaning that energy is transferred out of the system. So I like to think about this as being a stabilizing process. Because if our system is releasing heat, it's getting energy, out of the system, pumping it into the surroundings, then that means that we are going from a high energy state. So we've got our highly reactive, right, halogen gas and group 1A metal, going to our relatively solid or stable solid sodium chloride, which is, something that hangs around for a while. So because we've got this exothermic standard heat of formation, we have formed a stable compound. So let's maybe look at another example. I don't know, why not? How about the standard enthalpy of formation of water from its constituent elements? So let's start by looking at kind of our balanced chemical equation. So water is made up of hydrogen. The elemental form of hydrogen is homonuclear diatomic hydrogen gas, and also made up of oxygen, which is another one of our homonuclear diatomic elements. And if I were to make water from hydrogen and oxygen, H2O, yes, Then I would need to balance this equation because while I do have two hydrogens, I am left with only one oxygen on my product side. So I would need to double my water. In turn, I would need to then double my hydrogen. So this is kind of the I don't know, balanced equation that you and I would normally deal with. But remember, if we're looking at the standard heat of formation, we've got to look at the formation of 1 mole of our substance, so that's 1 mole of water. So if I were going to look at the formation of 1 mole of water, I would need to divide all of these coefficients by 2. So this becomes 1 hydrogen gas reacting with half oxygen gas to form H2O gas. And based on the table that's given here, let's see if we can't find it. So let's see here. Water, water, water. You've got to be somewhere. Okay. Notice, zoom in here. There is a distinction to be made between what phase of water or what phase of a substance is formed. So here we're looking at the formation of gaseous water, water vapor. And based on my table, we see that the standard enthalpy of formation, or meaning the heat that is evolved as a result of 1 mole of water being formed from its constituent elements, is negative 241.8 kilojoules per that 1 mole. Okay, let's do kind of one more example where we maybe take this just tabulation of standard enthalpies of formation and do something interesting with it. Let's see here. Consider the formation of, I don't know, let's pick something here. Let's do, for funsies, hydrogen chloride. No, I can't even see that because I wrote over it. How about we do, instead of hydrogen chloride gas, let's do methane gas. So this would be elemental carbon coming together with elemental hydrogen to form gaseous methane. To balance, I need to double my hydrogens. That leaves me with 1 mole out front here, so I don't need to manipulate my coefficients. And I know from my table that the standard heat of formation, meaning if I were to form 1 mole of methane gas at standard conditions, would be negative 74.8 kilojoules per mole. Now, why is this useful? What if I don't know, 8.6 moles of methane are formed? How much heat is made as a result? And then if we assume we're at standard conditions, then we can use this standard heat of formation as a conversion factor. So our standard heat of formation says that in order to form 1 mole of methane at standard temperature and pressure, that is going to release 74.8 kilojoules of heat. So this now becomes a conversion factor. And again, this comes from just the language of per, right? Kilojoule per mole. This is what allows us to be a conversion factor. So let's start with our actual mole quantity of methane that is formed. I know that if 1 mole of methane is formed, then 74.8 kilojoules of heat are released. That's what that negative sign means. So I need to take now my 8.6 moles and multiply it with my 74.8 kilojoules of heat released. So 8.6 times 74.8. This gives me negative 643.28 kilojoules released. All right, so this is the standard enthalpy of formation. I will always have to give you this table here if I am going to ask you to utilize these heats of formation. So these reference values will be provided because it's these values that we're going to need to use in order to determine, again, what's our goal here? The heat of reaction. So in our next video, we are going to look at how we can calculate the heat of reaction at standard conditions based on the heats of formation of acetylene. So we will look at that example coming up next in video 2.